This video is about tropospheric ozone chemistry, part 1. We're going to distinguish between tropospheric and stratospheric ozone, write the reactions of the primary photolytic cycle, and apply the pseudo-steady-state approximation. Ozone is bad for us. It damages our health, materials, and the ecosystem. But ozone in the stratosphere is good because it protects us from UV radiation. So there's a mnemonic good up high for ozone in the stratosphere, and bad nearby for ozone in the troposphere down low. The National Ambient Air Quality Standard for ozone is 70 parts per billion. The natural background is 30 to 40 parts per billion, even where people are not around. And we write kind of the general reaction for forming ozone as VOCs plus NOx plus H nu, representing the energy of photons, forms ozone. This shows the typical diurnal pattern of ozone in a polluted city in Northern Virginia and then in a rural area in Shenandoah National Park. So with the ozone shown in blue, you can see at midnight it's around 20 to 30 parts per billion. It actually decreases overnight below background levels due to reactions with NO and NO2. And then it starts increasing in the late morning as the sun comes up and there's some fresh emissions to help drive its formation. And then we see a peak that occurs in the mid-afternoon, and then it starts falling off again towards the evening. In contrast, in the NO and NO2 time series peak during the morning rush hour, and then they drop off. There is another slug of emissions that occurs at the evening rush hour, but we don't see it as much because the mixing depth has increased and there's a lot more dilution, whereas in the morning there's usually a very shallow mixing depth, and so things can become quite concentrated. And in contrast, in Shenandoah National Park, which is a rural area with very little NOx, there's a kind of a steady concentration at 40 to 50 parts per billion over the whole day. Over time, over the past 40 years, ozone concentrations have come down nationwide. The black line shows the average of measurements at sites across the US, and the shaded area shows the range of those. And you can see that it used to be above the National Ambient Air Quality Standard until around 2010 or so, and then we finally dropped below it, but we're not much below it. This map shows the non-attainment areas for the 8-hour ozone standard. There's large parts of California and many major cities are out of attainment with the ozone standard. The primary photolytic cycle describes reactions that maintain the balance between ozone, NO, and NO2. The first reaction is the photolysis of NO2. So we have NO2 plus energy of a photon, H nu, breaks up into NO plus O. And the rate coefficient for that is J sub NO2. We use J's instead of K's typically for photolytic reactions. And the value of JNO2 is around 0.5 per minute, inverse minutes. And it depends on the sunlight. So it varies over the course of a day and over the seasons of the year. It's higher in summer than in winter. The second reaction is that the O that has formed reacts with oxygen, the molecule, in a termomolecular reaction to form ozone. And this has a rate coefficient we'll call K2. And the third reaction is that NO plus ozone gives us back NO2 plus O2. So the net here is nothing. This is a cycle. And the rate coefficient there is K3. We're going to write some reaction rates here. That the photostationary state relation allows us to solve for the steady state concentration of ozone as a function of the rate coefficients and the concentrations of NO and NO2 from the primary photolytic cycle. So what we're trying to do is we're trying to find the steady state concentration of ozone in that cycle. So the first thing we will do is to write an expression for the rate of change of concentration of NO2, which is dNO2 dt. Now that's formed in reaction 3, and we lose it in reaction 1. So I'm going to write the rate of formation from reaction 3, which is K3 times NO times O3. We lose it in reaction 1, whose rate is JNO2 times NO2. Now the characteristic time for this reaction for the NO2 is around 2 minutes. The second thing we're going to do is write an expression for the rate of change of oxygen by itself, the oxygen radical, as a function of time, and that is formed in reaction 1, and we lose it in reaction 2. So the rate of formation gives us, from reaction 1, JNO2 times NO2, and then we lose it in reaction 2, whose rate is K2 times O times O2. The characteristic time for the oxygen radical here is around 10 microseconds, much smaller than for the NO2. Now we're going to apply the pseudo-steady-state approximation, or PSSA, which says that very reactive species, often radicals, are consumed as fast as they are formed. They're also at low concentration, so we can assume that dc dt, the change in their concentration as a function of time, is equal to 0. Again, that's because as soon as we form the oxygen radical from reaction 1, it gets consumed in reaction 2. And you can see that because the tau for it, the characteristic time, is 10 microseconds. Now, because of that, we can assume that dO dt equals 0 by the PSSA. Then we can take equation 2 here and rearrange it and solve for O. We get that O is equal to JNO2 times NO2 divided by K2 times O2. So again, what I did is I took reaction 2, I set it equal to 0 because we said dO dt is equal to 0, and then I had an algebraic equation that I rearranged and solved for O by itself. Now the third reaction that we're going to consider is for ozone. So we're going to say that dO3 dt is equal to K2 times O times O2 because it forms in reaction 2, and then we lose it in reaction 3, and the rate of that is minus K3 times NO times O3. I'm going to now say that we're going to make the steady state approximation for ozone because we said in the very beginning that we were trying to solve for the steady state concentration of ozone. And so I set this equation equal to 0, and I rearrange and solve for ozone. And I get O3 equals K2 times O times O2 divided by K3 times NO. Now I'm going to substitute the expression for O that we just found using the PSSA. It was O equals JNO2 times NO2 divided by K2 times O2. So it's what was at the bottom of the previous slide. So if I make that substitution, then I get that ozone is equal to JNO2 times NO2 divided by K3 times NO. This is the photostationary state relation, or PSSR, and it tells me that ozone is proportional to the ratio of NO2 to NO. So if I have more NO2, then I'm going to have more ozone. If I have more NO, then I'm going to have less ozone. So let's look at the next question, which is if NOx emissions consist of 95% NO and 5% NO2, and the NO2 photolysis rate is 0.5 per minute, and K3, the reaction rate coefficient, is 27 per ppm per minute, what is the steady state concentration of ozone? And this would be in the fresh emissions right away before much else happens. So we can apply the photostationary state relation and say that ozone at steady state is equal to, it was JNO2 times NO2 divided by K3 times NO. And so this equals, now we just substitute, our JNO2 was 0.5 per minute. Our NO2 to NO ratio, I'm going to write this all together. So we don't know exactly what the concentrations are, but we have, for NO2, it was 5%, and for NO, it was 95%. So I'm just going to write that ratio. And then, and remember these square brackets indicate volumetric or molar concentrations, so we can do that. And then we have K3, which is 27 per ppm per minute. And that equals 9.7 times 10 to the minus 4 ppm, which is around 1 ppb, which is pretty low, remember, because the background, natural background is 30 to 40 ppb. So in very fresh emissions of NOx, you have very low concentrations of ozone because that NO2 to NO ratio is pretty low.